Up to yesterday class, we have discussed about packet structure, RGB model, and then data interleaving and frame formats. How these frame formats are transmitted through from the transmitter section to receiver section. So all these things we have discussed. And then today we will go through that CSI RGB image data formats. So how not only image RGB, we will go through that YUV model and then what else? Raw model also we will go through that. See what is the RGB data type it is doing here. RGB means red, green, blue. Okay, that is the meaning of RGB. So suppose you think about your camera is producing too many images. So this is my camera. Okay, that camera is producing too many images. That means it is like a factory. Okay, this factory is producing some colored pixels images. That pixel image. Huh? Yeah, yeah. Not sharing. Okay, okay. Just give me a minute. Yeah, yeah. I'm sharing the screen. Now you are seeing my screen, right? Hello. Hmm. Okay. See, RGB model, how the data is transmitting from the transmitter's camera to processor. Because camera is like a factory you are thinking about it. This camera will be transmitting continuous images. Okay, that means high speed data it is transmitting. That transmitting from the camera to processor or display. So that is the main process we are working here. So maybe is the work we are doing here. Okay, that means we need to transmit the images from the processor camera to processor. For that, different type of RGB models are there. See, these are different data types 20, 21, 22, 23, 24, 25, 26, 27. So that means we have different bits. All these bits are having different type of data types related to RGB. RGB 444, RGB 555, RGB 565, RGB 666, 888. Okay, so based on this data type, we are transmitting the image from the transmitter side to receiver side. Suppose I'm thinking about it, general packet rule, how the transmission is happening. That means each line, how we are transmitting the data. Okay. Based on this RGB model, if you are thinking about RGB triplet model, in this triplet model, you are transmitting R is 8 colors, R is having 8 bits, and then green is having 8 bits, and then blue is having 8 bits. Total how many bits we are transmitting? 24 bits we are transmitting. Okay, so 24 bits means 3 bytes you want to transmit. Okay, 3 bytes grouped together, that will be converted into single packet. All these packets are transmitting in the payload. Okay, so that is the reason we are considering the RGB model. So in this RGB model, we will transmit multiple RGB formats. Okay, that means one image. Suppose bigger image you want to transmit. That bigger image needed more data. So the highest quality, that is 1920 by 1080 is my image resolution. This large image I want to transmit from the transmitter side to receiver side. So for that I need to transmit more data, right? Data I want to transmit from the transmitter side to receiver side. Okay. So if you are using more, means your bandwidth also more. Okay. Then bandwidth is more means, and then you need more power also. The power we are giving more. Okay. So based on the image quality only we are transmitting the data. So this transmission is takes place like a line start, where starting, that means if you have a frame, in that number of lines will be there. This is my frame. Okay, number of lines will be there, depends upon the, okay. then you need to check that where you are starting, that is where is my line start, okay, and then what is my packet header, what type of things are there in packet header. In the packet header we are having data type and then ECC and then word count, all these are there, and then payload of data you are, what type of data type you are transmitting. That means you are transmitting RGB data. So in this RGB data your model or triple five model, okay, any type of RGB data you are transmitting. That means one packet information. So these many bytes of data you need to transmit, because you are transmitting 20. Okay, this is your pixels. Okay, and then you are using RGB triple eight model, 8, and then G is 8, and then B means total 24 bits. Okay, that should be converted in bytes for 3 bytes we need to transmit. So 3 bytes into 1920, we I have explained in the yesterday class. So just go through that. So that means 5760 byte to transmit. Okay, these many bytes transmit for one line. One line, that means one long packet. These many bytes of data you need to transmit. So similarly, this RGB model and B1, G1, R1 is considered as a one packet or one line, and then B2, G2, C2, R2 is considered as a one line. So based on that, we are transmitting the data through the payload. Okay, so then packet footer means where packet, that will tells you that, and then lines, all the lines are transmitted means your line will be ended. Okay, see here RGB triple eight, for one pixel I want to transmit, so 3 bytes I need to transmit it. Okay, 3 bytes of data required, then only one pixel is transmitted. See, pixel B naught, G naught, R naught. Here there is a rule called RGB order rule is there, that we are transmitting RGB, that is the RGB model, but B is transmitting first. LGR model we are transmitting, because into displays or other cameras, okay, they are connecting many internal cameras or internal displays we are connecting. So that is the reason they are having some data we are having, that will be mapped with this BGR. That's why LSB is transmitting first. Okay, first, after that green, after that red. Okay, in this way it will be flipping the at the receiver side. Okay, that will be connecting, because suppose you are capturing the image, your eye is capturing the image. That means that image will be the reverse way. Suppose you are taking one image, that camera will be taking, this is your image, but your eye is like taking this way. Okay, reverse image it will be taking. That's why this also RGB data also reverse way. That means flipping way it is transmitting. That means lowest data it is transmitting first. Okay, so how it is transmitting means, see B naught, B1, B2, B3. So these transmitting first. That means each color, how many combinations are there means 2 power 8. 2 power 8 means 256 combinations are available. Okay, so based on that, it is transmitting information. So this is the pixel to byte packing format. So this is the packet size constraint we are having, and then how the transmitting. So this frame is having frame start and then frame end. In frame start and frame end, the payload will be there. This payload is transmitting the RGB model data in each lane of packet data. So, and this is another lane, this is another line, different lines of data we are transmitting. Okay, are you getting my point? Any anyone having any doubt in this? Huh, yeah, these models are fixed. No, this MIPI protocol, this RGB models are fixed. This MIPI protocol, RGB 444 data types are fixed. YUV model, RGB model, and then RAW model. So these models are implementing. Based on that only, we are transmitting the data. So, hmm. so uh, then if you are going to work on Ethernet means then their format is different. CSMA will be there, carrier sense multiple access will be there. In that carrier sense multiple access, how the data link layer is transmitting the data. You need to think about the data link layer, how the data will be transmitted here. Okay, so how we are converting whatever the image, whatever the domain name you are entering into your laptop, how it is converting into IP address. So that will be taken care by the Ethernet. So in that Ethernet, the bus function modeling is there. So it will be full duplex mode. So the data will be transmitted parallelly or receiving that. Based on that, it is operating in a different way. So that is different. And then if you are working on the memory, sorry, hmm. No, in spec they will mention. Yeah, in specification they will mention. In specification you can use RGB triplet model only, or use RGB triple six model only, or you can use RGB 4444 model only, or I want to transmit the data RGB model and then some and then raw data model. All these three things, that is the user data I transmit, depends upon the data, what type of data you are transmitting. I have shared it, right? Yeah, I have specification. Specification, I have just checked that group. I have shared the specification and then PPT also. So along with the PPT, I have shared the specification. You go through that specification. MIPI, MIPI specification. See here, MIPI triple six. Hmm. 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 Yeah, some of the specifications will be open. Yeah, very confidential specifications that is related to real time project. And then some usual specs are there, like MIPI. Some MIPI alliance will be providing some spec. Based on that spec, how it's implementing the real time camera. So they will implement that, they will modify something in that original spec. Okay, based on their requirement it will be modified. That confidential spec we will not get. Yeah, clear. Yeah. Same thing, RGB triplet model we are using. Triplet 18 bits we are transmitting. This 18 bits means, so that is not aligned with 8 bit, right? 16 bit, that is not aligned with that. Okay, so then there is a problem. Just give me a minute. Why this pen is not properly? No. See RGB triple six model. So for that I'm transmitting 4 pixels combined together. Suppose because 4 pixels making the 4 pixels means, so 18 bits we are taking. So this 18 should be multiplied with 4 means what is the value we will get? So 32, I think 72, right? So 72 bits you need to transmit. That means 9 data for 4 pixels. These cells are grouped together, combined like a packet. Okay, so that means BGR1, BGR2, BGR3, and BGR4. All three are grouped together and then will transmit in one packet. That means 4 cells we are transmitting like a one packet. That is the RGB model, RGB triple six model. Because this triple 18 bits only we are having. Okay, this 18 bits is not fully bytes for conversion, right? So bytes will be either 8 bits or 16 and 32 bits. Okay, only we are transmitting the data, right? So then based on that we need to multiply that. Here these pixels to bytes conversion will be packing here. So this pixel to byte, how we are transmitting, this is the B value, G value, and then R value. G is 6 bits, B is 6 bits, G is 6 bits, and then R is 6 bits. Total 18 bits. For 1 0 pixel you want to transmit, how many bytes of data you need to transmit? So 9 bytes of data you want to transmit. So that means this way to B9 data you need to transmit. Then only 4 pixels will be transmitted from the transmitter side to receiver side. Because why we are taking this byte alignment only means in the transmitter side we are transmitting anywhere, but receiver side how it is storing that will be the matter. Okay, so the memory how we are storing the data and then how the receiver is receiving the data, that is matters. If you are not following the byte rule means then we facing some problems like uh, data corruption or pixels mismatch. Okay, some bugs will be coming. Okay, so that's why some bits will be mismatched and some lower bits are mismatched with the um, other bits. Okay, this type of errors we are facing. That will be erased means you need to follow that. Okay, 8 bits are combined together will be 1 byte. And this RGB triple 65 means 16 bits. Okay, so why this green color is 6 means our human eye is very sensitive to light color, right? So then that's why green color is having compared to red and then blue, the green colors are green color bits are more. That's why see here also only we are transmitting 16 bits means 2 bytes of data. This is very much useful because it is aligned with the byte format. Then 1 pixel, how many bytes you want to transmit? 2 bytes of data you want to transmit. That means B0, B1 you can transmit means then these 2 bytes will be considered as a 1 pixel. Okay. See, this is 1 pixel, pixel 2. In this way, I am transmitting the data. See, this B this way it is transmitting from the transmit side to receiving side. Okay, so each packet how many bits are there means 16 bits are there. That should be 2 bytes of data combined together. And then triple five, if you are there is no problem, but triple five is that 15 bits only we are adding. That 15 bits means it is not multiples of 8. For that we are adding some. Okay, so these padding bits are not having any information, but align with the byte rule. You are sending the data from the transmitter side to receiver side with the byte aligned format only. Okay, so for that purpose, in that 565, we are sorry, triple five, we are adding some 1 bit padding bit. Okay, so that is the 16 bits we are transmitting. So padding 0 bit will be added here. Then 16 bits are combined together. Based on that, one data you want to transmit, 2 bits of data to 1 pixel you want to transmit, pixel 2 bytes of data required to transmit. Okay, and again triple four model. Triple four model means RGB triple. That is the lowest level because 12 bits we are using. That means R is 4 bits, G is 4 bits, and then is 4 bits. In that way, we are transmitting that. So then triple four model. Every time we need to transmit 12 bits for one pixel. You want to 12 bits. You want to you required to transmit the data from the transmitter side to receiver side. Okay, so that is the packet format. So we are arranging the bit because we need to follow the data types and then how many virtual channels we need to require to transmit the data, and then word count. All these things are there in your packet header, right? So that packet header will tells you that what type of data you are transmitting, and then payload will tell you what about that, what type transmitting, either RGB, YUV model, whatever it may be, that data. Okay, and then packet footer, what is it is having CRC, we are having. CRC means science check, it will calculate that errors. Errors are there, that means any packet mismatch is happened, that will be corrected at the packet footer stage. Then only the line will be ending, your format will be transmitted from the transmitter side to receiver side. Understood, all of you? Any doubt in this slide? Okay. So just go through this RGB model. You can take any example. Then how many bytes are transmitting for 444, 555, and then 888. Okay. So you can go through 20 by 1080 resolution. This is the your image pixels image representation. For this you need to calculate it. In the previous slide I have explained how to calculate the bytes for transmitting one line. In long packet, one line is transmitting. In that, how many pixels you want to transmit to complete one frame? Okay, to complete transmission of one frame. Okay, so based on, anyway, 1080 lines. Okay, so these lines are fixed here, but bytes may be varied, depends upon the data type, what type of data type you are utilizing. Okay, and then raw image transmission, this is also not a big deal here, because this raw image also having some fixed formats. That means image is transmitting, this raw image means what? Unprocessed sensor data we are transmitting. That means whatever the image you are taking, there is no processing. That camera sensors are capturing the image, or uh, here what we are going to discuss means how mobile is imaging that, and then how MIPI CSC is working for transmission of data through RG raw model. So all these things are discussing here. Okay, so what is that raw image model data means? That is a unprocessed data. Raw means is a unprocessed sensor data. That unprocessed sensor data may be coming from any sensors like compressed image or JPEG image, because there is no color combination here. So camera sensor captures whatever the captured image is there, that depends upon your light intensity. So for that we need to check your color correction, how the color is correcting. That means in before the line start and then line end. So before the payload, we need to check that what type of color you want to transmit, and then what type of thickness, white balance it takes. That we need to take care of that raw sensor pixels. Okay, so that raw sensor pixels is maybe sending some JPEG image or any type of image. Raw image means, see how we are buying some groceries, right? So this JPEG is like a processed food. Okay, so this food is means this raw will take care of that. So that means this vegetable sabji we can, based on that we can cook that. So that is the image process we are transmitting from the transmitter side to receiver side. So whatever the professional cameras are there, all these things are taking the raw image from the sensors, and then it will cook that. Then it will form that JPEG or MPEG image formats. We are having different type raw data model. So that is raw 6. Okay, 6 bits will be sending, and 10 bits up to 20. So up to 20 we are transmitting. See, raw 6, 7, and then 8, 10, 12, 14, 16. Okay, based on the resolution, your image resolution, these depends on this resolution. pixels will decide how many bytes of data you need to transmit for one pixel. Okay. See here raw we are using this raw 6 I need to transmit 4 pixels I need to transmit, then 4 into 6 is 24 we want to transmit. So for 24 bits are required to transmit 4 to 24 bits means 3 bytes of data. Okay, so 3 bytes of data, byte 0, byte n plus 1, 2. In this way, the data will be transmitted. So B5, B2, B1, B0. This is one image data. That means 6 bits we are transmitting. B5 to B0 is 6 bits. That is one packet. So one we are raw data we are transmitting. That means raw 0 and then raw 1, raw 2, raw 3. So 3 bytes you need to transmit means so 3 raws you want to raw 0 you can transmit raw 1 then 0, 1, 2 means 3 bytes of data. These 3 bytes will be transmitted for 4 pixels of data. 4 pixels from the transmitter side to receiver side. Similarly, you can take that raw 7 means 7 bits you need to transmit. That means for 1 pixel 7 bits. You need 7 bits. Then I want to packetize that, so then byte element is required. Then I have taken that 8 pixels, 8 sevens are 56, total 56 bits are required to transmit 8 pixels, 56 required. Then byte element should be 7 bytes of data we are transmitting. Okay, so that is a raw 7 model. So based on that, we will decide how many bytes of data we need to transmit for one pixel. Okay, not only one pixel, how many pixels you want to transmit for one. Okay, based on that, we will calculate this one. Okay, so whatever the pixel is, these are the pixels. For all these pixels, of raw data model you are using, based on that number of bytes will be varied. See, 3 bytes, 7 bytes, 2 bytes, 5. Okay, so these many bytes of data we are transmitting from the transmitter side to receiver side. Okay, so see, 8 bits means what are the combinations we have? 256 combinations are there, and 7 bits means what combinations will be there, and 10 bits means 102 there. Based on that combinations are different bytes of data. Okay, so this packet structure anyway you know that line start, packet header, payload, packet footer, line end. Line start where we are starting the frame, and then where we are starting the lines of your pixel. Packet header it will tell that type, and then id is also needed. Id means which type of data you are transmitting, and then is related to raw 0, raw 6 or raw 10. Okay, what type of data which one is transmitting we need to know that. Based on the id only we will know that. Okay, so if suppose you are talking 3 people are there, then who is talking means based on the name only I will identify that. Same thing here also id is required. See, and then yeah, these are the packing rules, how we are transmitting the data in the raw 7, 8, 10, 12. Okay, so based on that number of bytes we are transmitting here. Okay, so any bugs are there means that means some raw data is not properly aligned. That means is not there, then you are getting some bugs related to some pixels mismatch errors. Okay, so that we need to think about it. That's why byte alignment is very much important, because in the transmitter side we are transmitting any type of data, but receiver side is difficult. So suppose you are transmitting 10 taking, so this raw 10 means 10 pixels only transmitting. Okay, this data you are transmitting. Then one 8 bits you are transmitting 0 only. In byte 0 there is no problem. 8 bits are transmitting, but remaining 2 bits it will be sending in the next. Okay, that is the byte alignment is very much needed. Based on that, these 2 bits are related or first pixel or second pixel. I need to know that. That is the byte alignment we need to require to transmit the data. Okay. Through the code, we will. There is a UVM code. Okay, in that code, it will tells you which line you got the error and from which test case is failing. That will show that. Okay, you can go to that. Okay, why it is failing? We need to check each and every line. Okay, so based on that, we will think about it. Okay. Ah, theoretically, if you understand this one, easy. Yes, yes. Because mm, yes, yes, this packet pixels alignment, why it is aligning, all these things we know means then we will identify easily. Otherwise, it will be difficult to understand which one is not sending and which one is sending the data. So that will be identifying is difficult. Okay. Some user defined data are also there. So user defined data we need to transmit means so any type of data, either JPEG image or compressed stream or video, uh, some tapes will be transmitting. Okay, some user defined data means any type of data we are transmitting. Okay. So that is the user defined data. See, user defined data means what type of data you are transmitting. Okay, so that defines you either RGB data or YUV data or raw image data. Any type of data we are transmitting, right? That will be depends upon the user. So user may send any type of data like JPEG image they will send, or MPEG image will send, or compressed video will be sent. Depends upon the arbitrary of data. It is sending the different type of data. Okay. So user defined is also follows some raw I can say. Okay. Combining star 10 bits is sending or some RGB data it is sending. So RGB to image and then raw data is related to some metadata and YUV is related to UV video. Okay, YUV 4 I'm using that is for video. Okay, any type of data I'm transmitting here. That is the user defined data formats. Okay, by using all the data types, whatever the different data types we are having, all these data types will be transmitted by using this user defined data formats we have. Okay, UDFs are there. In this UDF, where we are starting the line and then packet header, in the different bytes of data typing. See B1, B2, B3, B4, B5, B6. So these many bytes of data we are transmitting based on the data type or image type we are transmitting from the transmitter side to receiver side. Okay, so this user side is having some conditions also there. So that means byte 1 and byte 2, byte 3, byte 4 and so on. So up to n number of bytes he is transmitting. In this all the bits will be aligned with byte format. So that means 8 bits it is transmitting B7 to B0. In the byte 0 you are transmitting and the byte 1 you are transmitting. So based on the image or video or compressed data, we will transmit different type of data. Okay, here it will tells you what does the image says from the transmitter side to receiver side. That means how the package format we are forming and then package structures we are making here. Different package structure, frame start packet, packet size, variable packet spacing. That means spacing is different. All these things are we need to look into it. Okay, while transmitting the data. Okay, so then here some example cases we have explained like JPG or MPG formats we are transmitting. Okay, so different data types it is utilized 30, 31, 2, 3, and then up to 378 8 bits are there. In each different user defined data types we transmit. In the byte 0 will transmit image. In the byte transmit video. In the byte 2 we will transmit some compressed data. Type of data we will transmit. Okay, so some thumbnails you are transmitting we are creating. Okay, that thumbnail we transmit is data type, or some depth information, some document you have created or screenshot you have created, that will be transmitted data type. Okay, so that is the importance of data type. So because we are transmitting the data in differently, always we need to consider byte format only. Okay, so because this byte format only we are and easily identify that which byte of data it is and who is transmitting this byte of data, that will be identifying easily. Okay, so if not byte aligned means you will get some actual data mismatch. That means you are adding some padding bits, right? That padding bits where you are adding. Okay, so that padding bits where you are adding, that will be identifying is difficult at the receiver side. So that's why most of the bits we need to take that some byte alignment format only. Okay. Hmm. 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 Every Yeah, they need to decide that they need to follow uh, specification. Based on the specification only, they need to design the RTL code. Yeah, yeah. Otherwise, if they designed something and then yeah, they provided some spec to us, and then we are reading that spec. But after reading the spec, we have created the test plan, but the test is not passing. We have checked all these things, but we need to check the design, how we designed for this, why it is not passing this test case. Okay, all these things we need to think about it. That's why the design, what he designed, based on that to release the specification. Okay, so see this. Mm, yeah, yeah. From that, see, they will provide some 1500 pages of spec. Okay, so then you need to study that 1500 pages of spec. So based on that, whatever the block they assign, they will segregate that some few pages only you will be allocating. You need to study that and sync up with team. Based on that team, they will also study that. Okay, so they will share the information. Based on that, you need to understand what they are studied and then how you studied, how you understand. So based on the discussion only, we will identify that. Okay, you understood in a proper way or a different way. Okay. Hmm. See, you need to check. Hmm. You need to check with all the like whatever that information is there, right? So all the things you need to know, and then if you verified all the corner cases and then stress cases and then back pressure cases, all the cases you have verified means, then still the bug is still there means you need to discuss with that. There is a chance to discuss. uh, Hmm. Yeah, I have verified all the cases. Uh, yeah, depends. First, we need to clarify. Yeah, yeah. Yeah, first we need to clarify our end. So our end is clear means then we can go to them. Then only they will listen us. Otherwise, they will scold us only. Hmm. 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 Yeah. Yeah. Hmm. Hmm. Yeah. Yeah. See, this is the storage, how we are storing the data because we are transmitting the data from the transmitter side to receiver side. So what how we are storing the data we need to know. So because what type of packets we are receiving. Okay, the transmitter will know that what type of packets we are receiving. Then only okay, so you are transmitting the data in the transmitter side in the byte aligned format, and then receiver side you are receiving the data in the aligned format only. Because see, I told you this RA10 model. Okay, so one data is there, byte 0 you are transmitting 8 bits in the one. Okay, so that means in byte 1 you are transmitting the to your next pixel data, then they need to align that. So and also we are transmitting 10 pixels, then uh, what is that 10 bits I am taking that, then you will consider 4 pixels, then only 40 bits will be there. So this 40 bits means 5 bytes data we are. So these 5 bytes of data will be packed one packet, then only it will transmit that. So these 4 pixels data will be combined together, then only small packet they will pack that, and then in that way all the pixels will be transmitted. Okay, so then only at the receiver side I will know that okay this is packet 0. Okay, this packet 0 will consider 4 pixels here, so 4 pixels data it is combined together, and again another 4 pixels data is there, and again another 4 pixels of data is there in packet 2. So based on that I will identify which type of data we are transmitting. Suppose 32-bit data you are transmitting, 32-bit word you are transmitting. That means we need 4 bytes of data. Okay, so 32-bit data you are transmitting means 4 bytes of 4 bytes we need to transmit from the transmitter receiver side. See how the restriction is there: RGB data, and then RGB 666 data, or RGB 565 data, 555 data, and then 444 data. All these data, see, based on the RGB, not only RGB, we can also have YUV model and then RAW model also. Based on that only, the receiver will know that. Okay, so this 32 data, this 32-bit data, byte 0, B1, G1, R1. How many bits are transmitted here? 24 bits. Again, another LSB we need to add, then only 32 bits will be transmitted here. See, B2 will be transmitted in the B1 only. In the first pixel only it is transmitted. Again G2, R2, B, G2, R2, B3, G3. So then this is the second pixel data, and the third data also combined together, and one it is. So based on that, we will make that data how we are transmitting. Okay, that is the memory mapping. Suppose you will take that RGB triple six means that is 18 bits. So 18 bits, how we are transmitting the data here? Here 18 bits will be converted into don't receive any see data is receiver buffer like 32 bit. Okay, so receiver buffer 32 bit it will be transmitting 32 bit only. See here 8 bits only there, so 18 bits, 18 bits will be converted into how many times here cells we are considered means 72, right? So 72, 9 bytes of data we are transmitting. That means G1 R1. So one packet, and then B2 G2 R2. So how many packets are transmitting here? 18 bits, 18 bits, 36 bits. Okay, but in that 36 bits, we are aligning that bit. So in the last R2 value, only 2 bits only I have considered. Okay, remaining 4 bits will be transmitted in that second packet format. Okay, then we can assign that byte format. See, byte 0 is that 1 down to 24. This is my 0 transmission. Okay, in the byte 1 also I'm having some 23 16 data I'm having. Okay, so this is byte 0 data, and then byte 1 again byte 2 some 15 down to, what is that, 15 down to 7 8 we are having, then again 8 bits, and then byte 3 0 1 2 3, so 7 down to 0. Based on that, data will be transmitted. Here 32 bits we will consider, so all this will be transmitted. But here, how, why we are R1 is transmitting, or B1 is transmitting, and B1 is transmitting, and then R1 is transmitting. But 32 bits are not completed. Here 24 bits only complete. Remaining 8 bits, next packet is also combined. Then B2 will be considered in the packet 1 only. That is the arbitrary model we are taking. Based on that only, we are transmitting from the transmitter side to receiver side. Okay, same thing we will explain in that YUV model also. So but YUV model is little bit complex. Why we are complex means, this YUV model, why complex means, YUV means Y is the luma. Luma is simply called as a brightness. Okay, so this brightness will be transmitting alternate, that means odd lines only we are transmitting. In the even line is aligned with chroma red and chroma blue. So this chroma blue is the differentiable blue. Okay, whatever the blue is there, so that blue is the differential blue. And then whatever the red color is there, that red color is also differential red. So that's why it is transmitting like, so in the odd lines what we are transmitting, V is transmitting first, and then Y1. After that U is transmitted, again Y2, in this way V1 Y1 U1 2, and then V2 Y3, okay, U2 Y4. In this way the Y luminous will be transmitted, so it will be sharing here. See how we are transmitting U1 by V1 Y2. Similarly, U1 Y1 V1 Y2 in the first 0th pixel and first pixel. So based on that number of pixels, you will transmit here. Suppose I will transmit YUV some 422 port, YUV 422. So 422 means how many bits are there here? 8 bits. So 8 bits are combined together. There is no problem. In that every data will be transmitted properly. But Y20, Y420 is there. YUV 420 is also there. This 420 is 6 bits only. This 6 bits will be multiplied with 4 bits, then 4 into 6, 24 bits. Okay, this 24 bits means 3 bytes of data we need to transmit. These 3 bytes of data, how it is transmitting means Y1, Y2, Y3 is that 3 bits. So total how many bits are there here? So each and every one 4 bits only. So YUV is having 4 bits. So Y is 4 bits, chroma is 2 bits, and then blue is 2 bits, chroma red is 2 bits. Okay, so here 0 bits will be there, but the fact will be added for 2 because of byte alignment. Are you on the same page, all of you? How I am transmitting the data? So this YUV data you will transmit like some alternative model we are having. So YUV 422 is there, and Y420 is there. Okay, we will transmit. This is YUV. So for this 8-bit data, it is transmitting. And again, YUV 420 10 bits data is also there. Okay, based on that, we will transmit the information. See, in the byte 0, so A2, A1, A2, and then A3. So 0, 1, 2, 3, 4, 6 up to 7 bytes, 7 bits we are transmitting. In the odd lane, what we are transmitting the data, YUV luminous data, that means Y data is transmitting, and then even lanes it is cycling with that, so that means combinedly transmitting. Combinedly, why it is transmitting means our eyes, human eyes doesn't see most of the brightness. That's why some colors will be added. So RGB you are added means R colors, total colors are added means you will get white color. Okay, you will get white color, and then all these are black color. But combining the two colors means you will get Y model and Luma, and then chromium differential red and differential blue will be happening. So we'll be creating here. Okay. So this differential blue and differential red, it will be neighboring of your luminous. That means brightness only. Okay. Brightness is nothing but luminous only. That's why U will be transmitted means Y is also beside of that, and V is transmitted means again brightness is that beside that one. Okay, that sampling data, two shade data we are transmitting. Okay, for one pixel, how many YUV data you need to transmit means U1 Y1, and then V1 Y2 also there. Okay, because of that we are combining the next pixel data also here. Okay, how we are combining that? Suppose one pixel you want to transmit, U1 is transmitting first. After that, even line, odd line, Y1 is so zeroth position. This is one position. Y1 is there. For one pixel, it is enough. But V1 is also there, right? So V1 is also transmitting. If you are transmitting V1 and again Y2 is also required. This Y2 is related to data, but it is transferred byte only. Okay, so that is the YAV model 420, and this 420 or 4 he will mention. So 10 bits you need to transmit or 8 bits you need to transmit, they will mention that. See, this YUV model 9 to 10, 9 down to 2. Why 9 down to 2 is taking here? So 8 bits only. And then again why 9 to 2? 9 to 2. 9, everything is 9 to 2 only. We are, and then other data, that means with luminance also getting the remaining 1 down to 0, we combining with the next data. Okay. So that is the ordering rule in the YUV model. So just check that YUV model how it is transmitting the 10-bit data, 8-bit data of YUV 420, YUV 422. So what type of odd lines we are transmitting, even lines we are combiningly transmitting that luminance and brightness. Okay, sorry, luminance and chroma bits, and then even odd number of lines only luminance will be transmitted. That means only partial data, that is the partial data we are transmitting here. Okay, same, this is also our raw model data, how it is transmitting the different sorry, different formats of YUV, RGB and raw data model. Okay, so check this slide also, how transmitting the data. See, you can see formats means you will get some idea. So these formats how it is dividing the bits based on the model. We 420 reception. In this 10-bit data reception, A2 to 9 only is transmitting Y1, and then B 2 to 9 it is transmitting to U1, and then C 2 to 9 it is transmitting for Y2. Okay, and then D 2 to 9 it is transmitting V2. Okay, in this way the data will be transmitted. See, Y1, Y2, Y3, Y4. Okay, again up to 7 violet luma colors will be transmitted, and then chromium colors again we need to transmit like U1, V1, V2, U2. In this way we will transmit, and then it is storing also. Similarly, raw data also. Raw data how will be packing in the transmitter side, and then how will be unpacking at the receiver side. This raw data will be taken care of that. Clear? So this is all about your mipi protocol. Okay. So you can go through each and every slide. Okay. So then you will know what data it is. Even and odd that both should be there in